Okay. All right, the recording has started.
Sounds good.
Beautiful.
And did you get this? Did you get the PDF that I sent that
Yes,
has
I
the
did.
outline?
I did get that PDF. Yeah.
Great.
Okay. So, welcome everyone. Scott Tooley is our fly of record for Team 11, and Tony Hewitt is our safety reviewer from Ezra. Grateful for him for his some of the feedback on progress reports so far, and for showing up today and reviewing our rocket and making sure we're ready to go. So, Tony, I had just kind of planned on you going through your questions and going through that checklist. We also have a brief presentation with some information on it. I'm not sure if you have a preference as far as kind of what we do first. We don't.
Oh, once you do
The
what?
presentation is kind of
If you want to do
supplemental, so.
if you want to do the presentation first, that might answer a lot of questions.
Mhm.
Kind of front run some of them. That way I don't have to spend time on those. So if you want to do that, that's fine by me.
Sweet. Share my screen then. All right. Can you see it?
I can. Yep. I'm going to just go full screen here.
All right. So we've got everyone over here. Oh, I guess I'll just briefly introduce a few others, some of the team that we've got here right now. So online, we also have Josh Taylor. He's our structures lead. And then here in person, we've got Aiden Rice. This is our GNC lead. Got Zach Lyman here, also on our GNC team. Have Brad Hornfisher. He is our systems engineering lead. And Taylor Anderton from our payload team.
Right.
And then I'm Nathan. I'm the team lead. So, all right, let's get into it.
Oops.
There we go. Okay, so we are competing in the 10K COTS category with a rocket called Alta. It's what our rocket is named this year, paying homage to some mountains here in Utah.
Okay, your screen sharing knocked off
Did
there.
it pause?
Yeah, I'm looking at the three of you guys.
Can you see it now?
Oh, now you got it back.
Yep. Okay, I guess when I hit the space bar, I'm not as familiar with Microsoft Teams then, so.
No,
Okay.
yeah, I'm not familiar with Teams either, so.
All right, as long as the recording's still going, that's what matters.
Yeah.
So we had a test flight, successful test flight already, nominal flight, nominal descent, nominal recovery. There were just mostly some scratches on the paint, which is why we didn't do a full paint job. So you'll see the rocket still unpainted right now. So just the cosmetic stuff is still need to be done.
A little bit of nose cone damage.
Okay. It's a picture of us at the test flight. Okay,
That's a beautiful looking test flight field you've got there.
Yep, that's up just south of Boise, Idaho. Tripoli, Idaho. They've got a site up there with a waiver high enough for us to go fly in. Okay, so it's a one-stage rocket, nominal diameter of 6 inches. Got 4 fins. Some of the fin dimensions: semi-span of 4.9 inches. Tip chord is 5. Root chord is 12. Fin thickness is 1/8 of an inch. The total vehicle length is 150 inches. Vehicle weight, just under 43, so 42.8 pounds. 10.25 pounds of propellant. We're on an M2500 Aerotech motor. Empty motor vehicle weight after motor burnouts, 59.3 pounds. Payload is 9 pounds. Brings total liftoff weight to just under 70, so 69.6 pounds.
All right. Do you recall what your thruster weight ratio was?
Thrust weight ratio is 8.
Okay. All right.
Okay.
I would just for future reference, I would not be surprised to see that number go up in the future to a minimum of thrust to weight ratio of 10. So for any returning team members, I would kind of plan on that. We're looking to get a minimum of 100 feet off, 100 foot per second off the rail. A lot of teams had a hard time meeting that based on kind of just, keeping past designs. And so just keep that in mind going forward, that next year we're probably going to look for a 10-to-1 thrust to weight ratio and or minimum, which is about what it takes to get 100 foot per second off the rail. I don't recall. I remember if you guys were a little low on the speed off the rail. Is that right?
Yeah.
Yeah.
So next year,
because it's hard.
next year, minimum of 10. Good to know.
I would say it's and may not be hard coded, but if you have a 10-to-1 thrust to weight ratio, life is just going to be a lot better. So I would kind of start planning on that. No one ever says, I wish I had a lower thrust to weight ratio, especially in the wind, which is almost always windy at the Spaceport Cup. So
That is true.
yeah.
Hey, that's good to know.
Yeah.
Remember that for next year. All right. Static margin is 1.79. Current simulated apogee is 10,017 feet.
Is that the average wind scenario?
Yeah. That's using the average wind speed and weather conditions at Spaceport America.
For June 19th
Yeah, for during the competition.
at noon.
Okay.
Okay, so yes,
Yeah.
the rail exit velocity right now is simming at 90 feet per second.
Yeah. And
That is-
that's not terrible. We've had people that are down in the high 70s, and that's really problematic. So you guys
Yeah.
at 90 feet per second, that's not terrible.
Not too bad.
I
Yeah.
will say,
No, that's not.
we do sim with we sim across the whole range of potential wind velocities, and we also the test flight, the wind velocity was about 11 miles an hour, so it was still it was still negotiating some wind, and it was able to handle it all just fine. Part of our design philosophy has been resistance to changes in wind velocity, so it's pretty robust.
Okay.
Cool. A few other of these numbers, like max velocity is just under 900 feet per second. Main deployment velocity is at 74 feet per second, and ground hit is at 23. There's a thrust weight, max acceleration about 8.7 Gs, motor M2500. Then our center of pressure and center of gravity are 103 and 92 inches there from the tip of the nose cone. Those are currently not marked on the rocket, but they will be once the rocket gets painted.
Okay.
So for
Yeah,
the actual competition, they'll be marked.
Okay. Something else just to keep in mind. One thing that we have to do this year is launch at a minimum elevation of 4 degrees, and we have adjustable azimuth pads. We've updated the pad so we can change the azimuth. So the launch angle will probably be into the wind, but there are some instances where it will be with the wind, there's a lot of reasons for that, and it is what it is. And so one thing that I'm kind of recommending teams do is look at the velocity, the apogee deployment velocity. If you have a 15-mile-an-hour wind and you have a launch angle of 4 degrees into the wind, and I think you'll be fairly surprised and or alarmed by the deployment velocity, because you're going to get a lot of horizontal velocity, as the rocket arcs into the wind, because you're already pointing into the wind. And even though you guys' rocket has fairly small fins and fairly low margin of stability, relatively speaking, but okay, it shouldn't weathercock terribly. But 90 feet per second, the way to not weathercock is to have 120 feet per second off the rail. So that horizontal velocity at deployment is going to be pretty substantial, and that's not true. That's true for all the teams. Less true, the faster velocity off the rod, the less weathercocking. But so just verify, just double check, maybe run some sims, and it should give you an idea of what the velocity at deployment will be as you arc over, and then do some stress calculations based on the amount of shear forces and snatch forces you probably will see from that. The number one failure that we saw Last year was rockets not separating because of that high velocity, the high horizontal velocity, and or failing because they deployed at 150 feet per second and things just weren't ready. They just weren't expecting that. So that's that's just something I've been telling all the teams that I'm reviewing. I know it's kind of late in the game, but some of these changes we're doing that to accommodate the Spaceport Cup folks or the Spaceport America folks. It's kind of what they're some of the limitations they're putting on us.
Yeah. So you said that there'll be an azimuth of minimum 4 degrees.
Minimum of 4 degrees off vertical. So, and it could go as much as 6 degrees. So, so you're going to be launching anywhere from 84 to 86 degrees, or the 4 to 6 degrees off vertical. I'm hoping that we never have to go more than 4, because nothing good happens. Obviously, every degree increases that horizontal velocity by that much more.
Yeah.
But just so just to be, I just want to make teams aware of that.
Yeah. And then we'll be launching. Well, you said some of the pads are into the wind, some are with the wind.
Well, no, it depends on the it depends on the direction of the wind at the time.
Okay.
We've run about 1 million, and I'm not kidding, about 1 million Monte Carlo simulations of wind direction and speed, and to get the rockets to land, if they have a ballistic trajectory, no parachute at all, we need to predict where they're going to come down, and in some instances, depending on the direction of the wind, we may actually launch with the wind so that they kind of arc back over towards the, just to kind of control a ballistic flight with a little bit more accuracy. Not that you can ever be super accurate with a ballistic flight, but that's just the thing. So just something to kind of think about in terms of the recovery. Your apogee deployment forces might be a lot stronger than most teams have been expecting. I'm hoping that's not the case, but
we were simming with a rod angle velocity of 6 degrees. Or rod angle of 6 degrees.
Yeah.
So
that's great. Okay, I'm really glad to hear that. So that won't then you guys aren't going to be. I have some teams that have never they're new, they don't know any better, and they think things go straight up. And they have a lot of folks have this thought that it goes up, it stops, and then comes back
Just
down,
falls.
and of course,
yeah, parabolic.
The test launch was
wasn't it at 6 degrees?
That was at 1.8 degrees. From the rail.
Yes, that was because the rail, the base we got donated to us and was not adjustable, so it's about a 2 degree angle. But yeah, we're simming with 6.
Okay. And one thing I like about the Blue Raven is that it gives you the horizontal velocity at deployment, which is really nice. And some teams that have used that have been super shocked by the speeds they're saying, because they're thinking anyway. So just a heads up on that.
Okay, yeah, that's good. We'll definitely run a few more simulations just to confirm before comp. Okay. So yeah, flight narrative. Here's some info about the parachutes right here. 144-inch main. Both shot cords are 50 foot. We'll go over kind of the materials and some more details about that later. Deploys at 1500 drogue. Deploys just at apogee, 48-inch. The descent rates here. These are average descent rates between deployment and then the end of that mission phase. So the average main descent rate is 23.1 and average drogue descent is 77.6. Okay. Here is some information that will answer the questions about structural things. So the body tubes, inner tubes, and couplers. Those are all made with carbon fiber prepreg, rolled on aluminum mandrels, and cured. And then there's some post-processing, wet sanding, cutting to size, layered with epoxy, and then sanded again to smooth and polished. They are attached, all the body joints are attached with bolts that are screwed in and nuts on the inside of the tubes. There's 4 bolts and nuts per joint section, and those are spaced at 90 degrees from each other in a circular plane there. that is orthogonal to the rocket's vertical axis. The inner tube on the motor section is attached to the booster body tube with 3 wooden centering rings. And those wooden centering rings are each 1/2 inch thick. And the motor retention bulkhead at the top, the forward end of the motor tube, the inner tube. That's also 1/2 inch wood with 1/8 inch carbon fiber plate, as well as fiberglass and epoxy wet lay over the inside of that to hold it in place. And after our flight, we inspected that retention bulkhead and could see no evidence of cracking or any kind of damage from the test flight. Rail buttons, there are 3 of them. They're Darlin plastic bought from Apogee. They're bolted through the tubes and with a nut on the inside. There's 2 on the booster section, so lower towards the aft. And then just because of our rocket's height and weight with stuff towards the top, we added a 3rd rail button, which is up towards the top of the drogue compartment, kind of about where there's a centering ring between the drogue compartment and the payload compartment. And that rail button is just right below that centering ring. So that's not going to catch a drogue chute or anything on deployment. The nose cone itself is a 6-to-1 von Karman. It's COTS filament wound fiberglass nose cone. So we can have RF signals from the nose cone from our telemetry system and GPS. The tail cone or the boat tail, 3D printed out of carbon fiber nylon filament and then layered with a coat of epoxy. And that's mostly just for a little bit for structural sake, but mostly for smoothness. So we can sand that and polish it smooth, just like the body tubes.
If you would like the surface roughness values, we have measured them, and we do have them.
We do have those
Now,
values.
well, and that's good to hear. More importantly, did you guys fly that tail cone on your test flight?
Yes, we did.
How did it survive?
It came back with no damage.
Yeah.
And we have another one as well printed just in case, but we've like drop tested it, stood on it multiple
I
times.
personally weigh about 270 pounds myself. I had the other one. I jumped up and down on it and nothing happened.
Yeah.
Good. Unfortunately, I've had a few teams who kind of were a little over enthusiastic with the length of the tail cone, and structurally that's an issue, but also the heating. They kind of got more heat at the bottom end of it than they anticipated, and they don't fare too well under that. So
This is
that's what I was kind of wondering.
Yeah. So these are the tail cones right here. This one is uncoated and painted. So the reason we chose carbon fiber nylon, and Josh, you might be able to correct me or elaborate, is just because it has better thermal properties and layer adhesion. Because, compressively, when you're orthogonal to the print layers, it can take a lot of force. But the big issue is if it like hits and there's a shear, then it's all about layer adhesion. Carbon fiber nylon has really good layer adhesion, which is one of the biggest reasons we chose it. Is all that correct, right, Josh?
Yeah, so like you were saying, it's got really good layer adhesion, and then it also has really good thermal resistance just because it's almost the exact same material that they use to actually make like Glocks and different firearms out of. So all firearms, polymer firearms, are made out of some sort of fiber reinforced nylon based polymer. And that's one of the reasons that we kind of thought of this, because we knew that would be pretty thermal resistant. We figured we could get some similar properties out of this. Obviously, our motors are going to be burning a lot hotter than just like a little like flash of like a cartridge going off in a firearm. But we figured it'd do a little bit better than kind of like the polycarbonates and the PET-Gs and the stuff like that we've tried in years past.
Yeah. And inspecting the one that flew, there was no evidence of melting or burns on the inside or outside in this aft rim. So we're pretty happy with the way that it turned out.
Yeah, that looks great. Yeah, very good. That's a lot of. I've seen a lot of 3D printed tail cones, and it often takes multiple iterations before teams kind of figure out what works. And the nylon carbon fiber, that's a great choice. And it looks like the overall structural integrity has held up really well. So that's good to see.
I will also say that manufacturing it additively was one of the only ways we could get the profile that we created by running a lot of CFD simulations with one of our partners. And so it just made that a lot easier.
Yep.
Yeah,
All right.
very good.
So moving on, the bulkheads, all of them are primarily made of a 1/2 inch thick plywood, and that was laser cut to the right diameter. And then almost all of them have carbon fiber plate reinforcement on them as well. Some of the bulkheads additionally have an inch of plywood, so two of those 1/2 inch plywoods epoxied together, and then the carbon fiber plate on one side as well, just for additional strength and fracture resistance. Those are especially the case on the avionics bay and anywhere that the parachutes are attached or there's a lot of mass attached. So they're pretty heavily reinforced. And we examined all the bulkheads and everything after test flight, and also we couldn't see any evidence of cracks or any kind of damage from that on there.
How powerful was the laser you used to cut your plywood?
That is a good
Any
question.
ideas?
That was the question.
How
It's just
powerful is the
not a big
laser?
deal.
Okay. I don't know. It's one
That's fine.
BYU has a laser here in our manufacturing lab. It's a CO2 laser.
Okay.
I don't know
So
the
it's, yeah,
power on it or anything though.
1/2 inch plywood is pretty decent plywood, and that requires a pretty beefy laser to cut through that.
Yes.
So,
Sim-
but 1/2 inch plywood with carbon fiber plate, I don't want to say it's overkill, but I have a fairly high degree of confidence that your centering rings are gonna hold up without too much trouble there. So
Yep, that's the plan. Yeah, we
yeah,
definitely have to mess around with the laser settings. I don't know the like powers, but they're like number settings that because sometimes it'll like burn the plywood too much
that's
on the
right. Yeah,
inside, so we gotta
yeah.
get that just right. But we got it. So
Yeah, we haven't been too conservative on our weight, preferred strength, because we're flying on an M2500. So
yeah.
Yeah. And yeah, I don't want to make too big a deal about that. And that's kind of how, as rocketeers and engineers and stuff, we tend to think that way. But that's going to be a bigger challenge in the future because as you try to approach that 10-to-1 or greater thrust to weight ratio, two ways to do that: a bigger motor or lighter rocket. And so,
Yeah.
those are all gonna, and 1/2 inch plywood is not light. Carbon fiber plate, obviously much lighter, but a lot more expensive, a little harder to work with. Although if you have, I wouldn't be surprised if you guys have access to a water jet. If you have access to that big of a laser, you can cut carbon fiber, obviously with a water jet. You've cut your fins, they look very good. So those are kind of some things to think about in terms of
Yeah. Going forward, even from this last year and the previous 2 years, we've learned a few more things about weight optimization. And then going forward in the next year, that's going to be one of the biggest goals.
we have found that one of the major causes in variability and altitude is the wind, and the change in wind while we fly, and that the heavier your rocket is, the better it is able to resist that. And if you have a longer rocket, you require less fin area that can be acted on. You get a little bit more consistent flights.
Yeah, see, well, yes and no, because and here's what I could show you, and I've actually made this video, I haven't distributed it yet, but I went through all the drone footage and have side-by-side shots of rockets that had high exit velocity off the rail and those that had a lower exit velocity off the rail. The ones with the high velocity, and it's super clear because you see the smoke trail, have nice straight trails. The one with the slower velocity and longer rockets tend to have a much more dramatic curve into the
Have a
wind.
more weather caution.
Yeah, and so all things being equal, speed is really your friend, because the faster the rocket, the less, when you have the two contributing forces, right? The alignment, the fins that want to make the rocket to go straight, and then the side, the impinging wind on it, and speed is one of the ways to counteract that. And I noticed that you guys, your fin span of your fins is really pretty small. Generally, the rule of thumb is one diameter of the rocket, and you guys are well under that. And that does help counteract some of that, but it also makes for a much less stable rocket. Now you guys are going, when I say less stable, at higher angles of attack, the smaller fin becomes very problematic. But you guys are staying below Mach, so none of that really matters. So so weight is good, but only if you can couple it with speed. And it's a very dynamic problem. And you guys have been there, and you know that. But still, it's always trade-offs. And of course, with heavier weight, then you got to have bigger parachutes and stronger components, and so there's all kinds of trade-offs that get done. But if the rules require that you go to 10-to-1, then nothing else really matters, because you got to get to that.
have to do.
I will say I would love to have just a more powerful motor generally for next year, because that gets you both. It gets you speed and it gets you mass and it gets you everything you want. There really isn't much more in the range of M that has higher thrust and higher impulse. I don't know if there are any that have both. But
no, I think the 2500 is pretty much it. Yeah.
Yeah. So
there's higher thrust
think,
M motors.
What was that?
There are two higher thrust M motors sold by Cicerone that can fit in Aerotech casings, but that's the next year thing.
Yeah.
Well, and those are kind of unobtainium, and so I don't want to say it doesn't matter, but until Cicerone can start making motors again, we're at the mercy of what we can get from Aerotech. And I mean, that's not a bad thing. It's great that Aerotech has these great motors available, but it's always nice to have more options, right? So,
well, in like 2 or 3 years from now, we might have a wrench getting thrown in this, because we are currently developing a hybrid motor at our university.
Yeah.
Good.
So,
well, that's great. Yeah.
Okay. Yeah, let's go ahead and move on to the fin attachment here. So like you're saying, the fins are cut out nice and clean. We use a CNC mill to cut those out of carbon fiber sheets. We're targeting CNC router, and we were targeting a thickness of 1/8 of an inch. We did some tests with different samples, and that turned out to be about 10 layers. Every other layer is offset by 45 degrees, so we could get roughly isotropic properties to be able to model the fins and the stresses in the fins more accurately, at least more easily. The fins are then epoxy to the inner tube in between the centering rings. Fiberglass is then wet laid over those for additional strength. And then the whole fin can is slid up into the booster tube with slots cut out so the fins can slide through the booster tube there. And then there's exterior fin fillets with silica reinforced epoxy.
It looks nice, yeah.
And we'll show you that in the actual rocket here soon. So a little bit more about the fins. Fin flutter, I know, is part of the checklist. So this is just a little bit about how we calculate fin flutter here. On this image, we use a laser vibrometer, measure resonant frequencies of the fins with hammer tests, and then that spits out the vibrational modes and damping of the fins, and then we put that into a MATLAB script, and that can give us the flight velocities that induce those modes. So our first mode and the velocity that induces that mode is about 2,200 feet per second. That gives us a safety factor of about 2.45. So that is definitely within the criteria that in the DTAG.
That's a great fin shape. I'm a big fan of that shape of fin that you guys are using. So
yeah,
it's a good fin. Yeah, it's a good shape.
I read a Pika Flight article that talked a lot about subsonic optimizations, and it essentially came down to trapezoidal is close enough to anything that it doesn't really matter. So
yeah, and it wouldn't take much if beefing up your fin stock to get your flutter speed up quite a bit. And so that's good. If you guys wanted to go to plus Mach and to 30,000 feet, that shape would still serve you pretty well, because you have that high leading angle to get out of the shock wave and this upswept to prevent it from being broken. You have, and overall that's a really just good, very serviceable shape all around. So
yeah, All right. And something we discovered that was very useful to us last year is this counterweight system. I'll show you a little bit about, I'll show you that on the mobile camera in a little bit. This is a photo of essentially what it is. It's a coupler section with threaded rods and then weights on those threaded rods. They're variable. So based on weather conditions and weather um, forecasts for time of flight, we can swap out the plates. Um, and that
Those are
is,
all the weights, by the way. We won't have all the weights
yeah,
on the rocket.
this is all of them that we have. And then there are also some corresponding ones in the nose cone. So we can adjust the stability as well. And that was also very helpful in the manufacturing process because when you're manufacturing, the beginning, some stuff is kind of unknown. So if you have a margin you can play with as far as stability and overall weight, it's very helpful. And that came in handy this year as well as last year.
So where's that located in the overall structure of the rocket?
So this coupler tube is just above the booster, in between the booster and the main parachute section. And then there are some cylindrical masses right up at the tip of the nose cone that are attached to the metal nose cone tip via the threaded rod that comes out the back of it.
They're pretty close to the
So being
center
the-
of gravity.
Okay, so it's not really going to be changing the overall
No,
DG that much then. Okay,
no. So
so it's really
this
just
this
okay.
main coupler is fairly close to the center of mass.
It
And
is
so it overall
slightly-
just changes the center of mass or it changes the overall mass of the rocket.
Yeah,
And then the one in the tip of the nose cone, it's just little itty bitty masses because there's such a large moment arm. And that is just able to kind of counteract any changes to stability that are given by this coupler section. Right. Like I mentioned before, M2500 motor. Do you have any questions about our propulsion?
Oh, do you guys have your hands on that motor?
We do not yet. It ships tomorrow from Cedar City. And so we expect it to be here sometime next week. What our
Okay.
vendor has said.
It's just at this point in the game, we're hearing people having a hard time. Motors that are supposed to be there for them aren't, and
Yeah.
and so
We had our
I just want to make sure.
I would
Go
say
ahead.
we had our test flight motor, but we used it and we were just waiting on this. But luckily, the motors that we had ordered are shipping just today or tomorrow, is what Aerotech has told us. So they should be here in plenty of time for the competition.
Great.
Especially because it's within the same state. It's only like 2.5 hours away. Okay, so a little bit about switches and redundancy. We'll go over this a little bit more detail later if you have any other questions, but we have two altimeters. They're both Blue Ravens. They're both completely separate circuits. They have their own switches, which are pull-pin switches, and they have their own batteries, and they go to their own their own E-matches and charge wells. And then we'll show you how that looks in the actual AV bay later. We have two GPS systems. One of them is the primary GPS. It's a featherweight GPS. It's up in the nose cone, as well as a SRAD GPS system with a Pixhawk flight computer as a backup GPS. They each have their own batteries as well.
I do have a question about altimeters. If we wanted to add
Yeah.
more for measurement, is that has there been any discussion about that? We talked to Perfect Flight about the accuracy of our test flights measurement, and they said that our range was to be expected, and it was about 100 feet of measurement error. I was just wondering if there's anything we can do to tighten that up.
From a contest rule standpoint, I hate to say it, I honestly don't know what the answer is. You can, as far as we're concerned, you can have as many altimeters as you want. Measuring, whether it's a accelerometer, barometer, or both, whatever. But in terms of what the submittable altitude and how that's calculated, I hate to say it, I am not the guy for that. I'm just the safety guy and the guy that helps get rockets on the rails. So one of the safety guys. So I don't know anything about the contest rules or any of that stuff. And I'm sorry to be ignorant on that, but it's just
No,
there's
it's
only
all
so
good.
much stuff we can each know, and I just don't. That's beyond my pay grade on that deal. Sorry about that.
No, it's all good.
Yeah, we can email
Yeah.
someone maybe or put it in the forum.
I will tell you that two things. The altimeters are affected tremendously by temperature. And so when I say that, the just the sensitivity of the baro sensor itself is affected by the temperature. And so if there's, differential heating between two altimeters, one's closer to battery that's maybe putting off heat, or closer to the wall, if it's a darkly painted rocket and it's right up against the, maybe getting a little bit of radiant heat, that could affect it. Light is your enemy. You don't want any light impinging anywhere near the baro sensor at all. I've seen some really cool baro traces where as the rocket spun and the vent hole allowed the sunlight to actually impinge on the baro sensor, you can see the altitude, you could count the rotations of the rocket. And so all of those things, and of course, they all use a model at 59 degrees at sea level as their base. And so as the air gets warmer, it starts to underestimate the altitude considerably by as much as 10% in some instances, depending on a variety of factors. So it's I have flown two perfect flight altimeters that were within 10 feet of each other on some flights. And on other flights, I've had similar kind of variation as to what you guys have experienced. So it really is, there's so many things that go into it. I honestly don't know. See, I don't even know if you can substitute GPS versus baro. So you guys got me on that one. Sorry.
Yeah, we have to use baro. But yeah, no, what you're
Okay.
saying makes sense because we were measuring a temperature at 80 degrees on the inside of the body, but the outside temperature was like 65 or 70. So.
Yeah. So yeah, it's a challenge. I would prefer to use GPS, but it is what it is. So
Yeah.
Cool. Okay, well that's helpful.
Yeah, that's good to know.
And paint the AV Bay white too. All right. Real quick about arming.
Barometers.
They're all pull-pin switches. They're all calibrated before launch and before assembly. Once the rocket's vertical, the telemetry is actually activated before the rocket goes vertical, just because there's no energetics or anything there, and we have to be able to establish link. And the pull pins are going to be too high anyway once the rocket is vertical. Then once it is vertical, we arm one altimeter at a time, listening to the expected readouts. You can check the app as well. It connects there. And then once all that stuff, got the proper readouts from the altimeters, everyone clears the area, and the igniter's inserted and continuity's checked, and we're ready to go.
Sounds good.
Okay, a little bit, a brief blurb here about the payload from Taylor.
Hello. Yes, so for a payload, we decided to work on additive manufacturing because it is an emerging technology for space travel and space flight. It's stuff that people are interested in using for space flight because you can produce parts on site instead of having to carry them with you. And so we built one to see if we could fit it inside of a CubeSat parameter and see what changes on the flight through the status of the flight. Yeah, so it's going to be inert for the whole flight, and then it will detect when it lands and begin to do its thing. So yeah, that's our mission profile is just showing that it's going to launch with the vehicle. It'll detect when it lands, and then it will execute its print while awaiting recovery. And then it'll be yeah.
That's pretty cool. Yeah, it's interesting.
Yeah, and so our assembly is pretty simple. We just got our standard assembly using the angle brackets, and we will surround the print area with a protective acrylic so that we don't damage the carbon fiber or cause any health risks to anyone recovering, just in case.
It's also UV protective too.
Yeah, it'll be UV protective, and we will have a pull pin to turn it off and on.
Yep. Then Aiden is going to talk a little bit about recovery here.
Yes. The arrow keys moving.
Yes.
Okay, so as mentioned, we're using 2 Blue Raven altimeters. And so in the picture on the bottom right, you can see one of them. So we have them on like either side of the 3D printed sled. And as you can see, they're kind of a little bit of ways away from where the pull pin hole is. So we're not really worried about light getting on them. We're just following, as far as wiring goes, just what Featherweight recommends for the
sorry.
wiring diagram.
Hey.
Yep.
Hang on a second here. I lost. It dropped out.
Oh.
Let me get you guys back here. Can you hear me? Okay.
Yeah, we can hear you.
All right. I'm not hearing you. Hang on. Maybe mute your audio and then unmute it.
How about now?
Now, shoot. Hang on here. Let me.
You don't have a microphone key then. Hello?
Yeah.
So
Hang
Might
on
be
a
on-
second because
might
I'm
be on
not getting
his
any audio from you. I'm not sure. The connection dropped for a second, and when it came back,
Scott or
everything is
Josh,
like
can you
your
hear
audio
us?
is like at 1
Yeah, I
speed.
can hear you. I can hear you,
Okay.
Aiden.
So I think it's on his end.
I can also
Um,
still hear you.
Okay.
Hang on here. Shoot.
Please.
I'm not sure how we can fix this.
Um,
Let me try turning my audio off and on.
gonna have to be somewhat quick because Scott has to go after 5. Yeah,
Guys, was I?
No, I'm not.
Can you hear anything, Tony?
You know, I'm gonna have to leave. Let me leave the meeting and rejoin. And when I come back, hopefully it'll pick up and record because the audio is just not behaving at all.
Like it's been transcribing everything so far.
All right, try saying something.
Can you hear me now, Tony?
No, dang it.
I stop sharing.
sharing network.
Not
Mike,
sure what
can you
else
hear me?
we can do
Hello?
here to fix this.
Microphone.
Yeah,
It's
the audio
picking
is
up.
completely messed up. It is. It's also you guys are aliens or something. It's like really it's like almost 1/100th speed slow motion, and it's it's nothing I've ever experienced before. Now Nathan, I assume you're the host. Your account. So I've already left. You know what? I'm gonna quit Teams and start back up. So give me about a second to come back.
My battery is low-ish.
Plug it in.
22, so let me plug it in.
I was gonna say you got a power strip right there, my guy.
Yep.
Or is it just that they don't like you?
Yeah.
As soon as we hand it over to Aiden.
Yeah, I just start yapping, and then the system
It would be
gives
pretty
up.
funny if
Bro.
like Aiden's
Bro.
voice was just the right frequency
See, to ruin the audio. Yeah.
Give it some malicious code through the audio line.
Yeah.
The only frequency here is the frequency of autism. It could smell it.
Yeah.
Okay, I rejoined through my browser, and that seems to be behaving better.
So can you hear me?
Yep. Can you guys
Excellent.
hear me?
Yep,
Yes.
we can hear
Yeah,
you
we
just
can hear
fine.
you.
All right, sorry about that. One of those
Nope, no
things.
worries. Well, we're just giving ourselves power here. All right. I don't remember. I set the screen sharing, so we can do that.
I feel like every time I touch something recently, I've been shocked. Maybe I swallowed a battery or something.
Right.
All right. Can you see the screen, Tony?
I can,
Good
yeah.
job. All right. Go
Okay.
ahead, Aiden.
So kind of, we've already touched on this a little bit, but we're using Blue Raven altimeters. And so that's being used for both primary and secondary. You can kind of see on the picture in the right, you can see the one Blue Raven, and then you see the battery, and then kind of the switch that everything's going into. The back of that sled also has the other Blue Raven, so they're kind of on opposite sides of each other. And so we're using lithium ion batteries. They're cylindrical and metallic casing, all in accordance with the rules there. They're 2 cells, so they're the 2 separate cylinder batteries connected. 7.4 volts, 2,000 milliamp hours. That's not the one depicted on this picture because we weren't comfortable with the lifespan of those. So we're gonna, and you'll see it a little bit here when we show you that we're gonna make the holes a little bit bigger for the batteries are slotted into to put the bigger ones in them.
Hold on a second here. So those are lithium, 2,000 milliamp hour lithium ion batteries?
Yeah, 2 cell.
Because the normal Blue Raven calls for 100 milliamp hour 1S. So that is that's like 20 times almost what the thing. So I have flown Raven starting from the Raven 2 up to the Blue Raven. And I've never had an issue with battery life. So help me. And the reason here's my concern. As you guys know, the lithium ion batteries are verboten by the new DTAG.
Right.
And so if they're if they're polyethol, they're for sure, when you guys show up, they're not gonna let you fly them. They're gonna, especially if it's a 2,000 milliamp hour battery, that's not gonna fly.
If it's lithium ion or lipo?
So when you say lithium ion, well, they're all lithium ion.
Yeah.
So lithium ion, lipo's a lithium ion, right? It's just they're lipoly, so they're all lithium ion. It's just, so when you say lithium ion, is it like so it's not a polymer based electrolyte.
No, it's like a typical lithium, like a typical lithium ion cell, like in like a Duracell battery or something.
Oh, okay. All right.
Not a lipo lithium polymer.
Okay.
Yeah, we have this one. So this is the ones that we ordered for it. So I guess the reason why we were kind of worried for it is because we've had previous experience, I guess, like last year where we were kind of on the pad waiting for, I don't know, like 3 hours before we launched or something like that.
We've had worse.
And have had worse. And so we remember reading in the Blue Raven manual saying that you can use larger batteries. That's okay because it limits the current that comes through it down to 4 amps. Yeah, and so we think that would be fine, but I mean we're open to suggestions if you think that the 7.0.
Let me see the battery package again. It's the
2 cell. Need to be closer.
So yeah.
Yeah.
Well, the key is, as long as you guys, here's my concern. As long as you guys are comfortable that they meet the DTAG rules, because all the lithium batteries are all lithium ion. I mean, that's electro. It's just how they're packaged, right? It's whether it's in a lipoly or it's more in a traditional, electrolyte substrate, like a AA battery type thing. So that's really the key. As long as you guys are comfortable, and you're right, Adrian did reprogram the firmware on the Blue Raven. I know if you're using a 1S, you can go to a large battery, but you might want to. But they're really designed to use a 1S, so yeah. And I think the current limiting will still be okay. But you might want to just do a little bit more research on that. And I say that because that's just a lot of milliamp hours
right.
to put behind that, especially if it's 2S, right? So so I would just verify. And I'm trying to think when because I've worked with Adrian. I was a beta tester for the Blue Raven, and the early ones could handle. The MOSFETs were rated for like 20, 25 amps, and people were still killing them because they were putting giant batteries behind them. And so you can easily do that, if you're dead short, especially a LiPo.
Right.
So so yeah, just make sure that you guys pass the D-tag and the battery isn't going to kill the Raven if it's a dead short on the on your EMAX. Those are because obviously if you kill a Raven at apogee, your main's not going to come out for that Raven, right? And if you've got the same battery on both and you kill both of them, then we've got real problems. Yeah. So
so I'm comfortable. I'm confident that it follows DTEG pretty well.
Okay.
And so
Good.
at least in that part, but yeah, I think we'll look into it more to make sure that we won't be overkilling it then.
Yeah.
So maybe I'm putting too much confidence in that statement saying you can use bigger things, but it can limit it. So it's like, okay, well, but we can, we can look at it.
Yeah, well, I know that testing that Adrian did were all, as far as I call 1S cells.
Okay.
And so that's the only thing that concerns me. Is that it's a 2S instead of a 1S. But as long and as long as you're comfortable and confident that you can, when you're in that hot room with all the people standing around and the safety reviewers like, oh wait, these things don't meet the D-tag, you can confidently and overcome anyone's objections. Like, nope, these things are perfectly okay. That's that's my main goal. I don't want you guys getting stuck at the safety review in the building and having to fight a battle. So
yep. No, yeah, that totally makes sense. So yeah, we'll look into that because I guess that was our main concern was going to the 2S was just getting more power behind it because we were wondering like, well, if there's a big delay and we're on the pad for a couple hours again, then if that doesn't last for a couple hours or whatever. So we can look into that more for sure. Yeah, does the rest of that sound good as far as the altimeter setup and the pull pins and the limit switches and all that?
Yep, that looks good. They're all completely independent. How have those switch connectors been working for you? I see you have the lever actuated switches, not Wagyu. I want to call them Wagyu, but whatever the heck those things are called. Have those been pretty reliable for you? And
yeah, we've been using them for the past few years for all of it, and I don't think we've had any issues for it. And like we make sure that the pull pin relative to the switch and the hole and all of that is like a good size, so they won't slip out or so they don't get stuck or whatever. So
you have switch rebound.
Yeah, and so that we don't have like switch rebound or anything. So it's like we're pretty confident in it, and it's been it's been a good system.
Okay, good. Lots of shear pins.
So 8 on main, 6 on drogue. And so we ground tested with it. You can see we have 7 grams of black powder for primary, 8 for secondary, 9 for primary, and 10 for secondary. And then it worked well on the test flight, so we feel pretty confident with those as well.
Good.
We had good separation. It wasn't close or anything. And then the sled itself, we're printing it out of polycarb, and then we have 4 vent holes, each a 1/4 inch diameter along the switch band.
So one thing that you might want to do is go back and look at the accelerometer data from the Blue Raven at apogee. And there's two things. I believe that you can still get the horizontal velocity because the Blue Raven, that's one of the things I really like about it. It gives the horizontal velocity at apogee. And look at the traces and check the G-forces that you guys are seeing when the charges fire. And really, that you guys have that 50-foot shock cord, if I recall. Look to see what kind of it's not really a snatch force, but just when it hits the end of that 50-foot shock cord, look at the traces to see what kind of G forces you're getting there and that they're within your expected range. A lot of teams are shocked. I used to have on multiple occasions I pegged the accelerometer on some of the altimeters because A, too energetic charge, B, too short of a shock cord, and when they hit, when it hit the end of that, it created a tremendous amount of force. And if it's in a nice linear fashion, that's good. But if it's at a high velocity and you're going sideways, that's when you can have like really nasty zippers and other bad things happen. So you might want to review that just to make sure that you didn't see anything unusual in your on your deployment.
Okay, yeah, we'll definitely take a look at that. Thank you.
Is there a preferred charge preparation method that you have?
Man, yes. Think of black powder was designed, and all smoke and powders are designed to be discharged in a long cylinder, and a long cylinder with a fairly narrow diameter, like an LD of 20 to 1. A length of 20, diameter 1. And people, if you watch slow motion black powder of how it burns, it doesn't burn. Everyone's always shocked by how it burns. A lot of the powder, depending, is actually ejected and burns in the AV bay, in the payload bay, not actually in the charge container. Everyone has this idea that it's an explosion. Well, it's not. It's very slow burning. And to burn well, it has to be contained under some pressure. And the way to do that is to have a long, thin gun barrel, right? If I put it in a pistol, and again, I've had people argue with me, and physics is physics, but if you take the exact same cartridge and you put it in a 3-inch, a 5-inch, a 7-inch, and an 8-inch, and a 10-inch barrel, the longer the barrel, the higher the velocity, because the more complete combustion you get of the powders. And that holds true regardless of whether it's a gun or an ejection charge. So if you think of your charge holder as a barrel, you want a fairly small diameter and fairly long, and you want the powder completely contained at the bottom under some pressure. And I've started putting the E-match on top of the powder instead of at the bottom, just because it's pretty easy to show that if you put the E-match at the bottom, the pop of the E-match itself will displace some of the powder forward and can create an additional problem. So if you put it at the top, you're starting kind of at the top down, which is not, which is the opposite of what a pistol does, but it's kind of 6 1 half does the other. So you want your black powder, you want something to, whether it's, I use Estes wadding because it's fire resistant to occupy that space under a moderate amount of pressure. If you reload black powder, firearms, you always have to have the black powder slightly compressed when you ignite it to get the best overall burn. And you want it to burn in a contained area, because the flame front, as it progresses, is what ignites the adjacent grains. If the space gets too big, the grains don't ignite, and you get and the black powder charge greatly underperforms. Folks have been shocked by, they'll use like an open fingertip glove in the bay, and then they put it in a tightly contained thing, and they need way less powder than they were using before because they're getting much better overall ignition. So more than you wanted to know, and sorry to go on, but it's that's what you want to get the best combustion. You want a long chamber, kind of almost what I have in my hand here. It's a long, thin aluminum pen that you'd have the black powder on here, and plenty of room for it to stay contained while it ignites to create a nice big ball of gas coming out the front. Now, the downside of that is that does create a pretty focused jet of hot air, right, of hot burning gases that you have to be careful aren't going to, run into anything that you don't want anything like a shock cord right over that. So you do have, it does create some other issues, but that's really the best way to get the most complete combustion.
Yeah. No, yeah, thank you. I think we have some pretty good charge wells relative to like using PVC end caps, but we'll go over that more when we go over the rocket. But yeah, that's very helpful.
Well, good. And the main thing, as long as you guys have ground tested and you've also flight tested and you've had good separation, that's important.
Yeah, for sure. Okay, so just moving to a little bit of recovery harness specifications. So we're using 1/4-inch Amsteel blue. It's kind of a proprietary thing from this company called Dutchware. It's made of an aramid fiber.
So that's super familiar with it. Yep. Okay, it's great. Dyneema, and it's great stuff. Actually, it's become really popular in our club. More and more of us are going towards Dyneema or Amsteel, and so that's good.
Yeah, excellent. So yeah, rated to 8,600 pounds for the 1/4-inch. Both of our parachutes, they're parabolic and they're made of ripstop nylon. The main parachute's 144 inches, the drogue's 48 inches. The main is red and silver, the drogue is pink and black. We're using fire blankets, and we're also using dog barf to protect both of them. And as far as like linkages go, we are using swivels for the shock cords to the parachutes. Those are rated to 6,750 pounds. We're using quick links rated to 2,200 pounds. And then we have our U-bolts, which are rated to 2,000 pounds, but we did some extra failure analysis on it. We put some in a tensile tester and kind of figured out, okay, it experiences complete failure around 19,000 pounds, experiences some plastic deformation at near 4,000 pounds. And so we kind of did some like, okay, the worst case load scenario of like if ejection at full weather cocking, we kind of got some of that acceleration data back from Open Rocket, and that's like 40 Gs. worth of acceleration. And so we're pretty confident, like looking at that and looking at these forces, that the U-bolts will be pretty good. We have give us a good factor of safety there. And same with the rest of the harness. So
a couple quick questions. How are you terminating your Dyneema, the amp steel? Because it really does not like knots, and it's really, and I'm sure if you've used it, you've seen plenty of videos on how to do the finger splice or the lock, and all the lock things, and use soft shackles and quick links and all that kind of stuff. And so that's really important. It's not a knottable. Using a knot is kind of counteracts the whole value of what you get out of that. So that's something to watch out for.
Yeah, that's good to know. We've been using double figure 8 knots onto the quick links.
Yeah, if you just Google using terminating Dyneema and you can amp steel blue, but Dyneema is kind of the more generic name for it. You'll see that it is almost always a finger trap style loop, and that's pretty much it. No knots at all. The other thing is dog barf. I have found, personal experience, it is depending on how much you have and whatever, it acts as a coolant and a shock absorber for your ejection charge. And I've had ejection charges that worked perfectly and never had an issue until I started using dog barf, and then they didn't. And when I did some testing, I found that the dog barf basically trapped and cooled the gases. And of course, the reason the gas expands is because it's hot, right? So if you cool the gas, if it has a chance to cool in that dog barf almost can act like a baffle if it's too tightly packed or there's too much of it. So just be a little, exercise a little caution on that. From a safety issue, we want to get that shoot out more than anything. Fire blankets are good, and there's nothing wrong with dog barf. Use sparingly and not huge volumes of it, because it does absorb gas and heat, and those are that's the opposite of what you want, right? Because you want heat and gas, because that's what's going to get stuff out. So just be careful with that. So
all about balance.
Okay. Yeah, that we'll make sure to keep that in mind. Thank you.
Okay.
Any other questions about hardware specs for the recovery harness or anything for that?
Nope, looks really good. It's really interesting to hear about your failure load. So that's quite a bit higher than I think most people would have expected. I'm sure. I don't know if you guys were pretty shocked by that. That's pretty surprising.
Yeah, it was. It was fun.
Yeah. Now, was that a sample of one, or were there multiple samples on that?
There's 2. So we got 2 extra, and then that's what they're both showing, about 19,000 pounds.
Wow, that's really interesting. Yeah. And honestly, based again on my personal experience and having done this for over 20 years and been to balls many times and seeing a lot of failures, it's extremely unusual to see a U-bolt fail. There's going to be some other weaker link before that U-bolt, and it's almost always where a cord is joined, like a knot or an eye bolt or something else like that. So,
right.
Nope, that looks good. Very good so far.
Great. As far as GPS tracking goes and the telemetry system in the nose cone, so I guess the telemetry system in the GPS tracker, the live telemetry system is SRAD. It works on 915 megahertz ISM band carrier frequency, so you don't need a ham license. We use the featherweight GPS tracker. That's kind of the primary one to locate the rocket, and then the SRAD one is kind of for the backup, but that's also just to get data and kind of mess around with telemetry. We've used the featherweight GPS tracker many times in the past, and it's worked great. So we're really confident with that, and we did telemetry last year. That also worked great, and so we're just refining that to make that better. So the interesting thing about this setup here is that the telemetry system is mounted to this aluminum bracket, and then this aluminum bracket is also what holds together the nose cone and the body tube. So it's kind of serving 3 purposes at once through the bolts that are in it. And so this is kind of the main consideration when we're looking at forces and stuff happening at the beginning of the rocket. So we did FEA analysis on it. Zach can go into some of the loading conditions and kind of how we did that more into detail. It survived the test flight, did well. We didn't notice any damage in the test flight around that area, and it was all very well and sound. And it fulfills the FEA pretty well. We also have an onboard camera, and all those have separate battery systems. So,
I will. Have you guys used the run cam very much?
we have used some run cams. I think the one we're using now is a run cam, right?
Yeah.
Yeah, the one we're using now is also a run cam.
So, okay, so one of the biggest issues we have, and I know some of you guys have been there before, but is the run cams and GoPros both tend to overheat.
Mhm.
And in fact, GoPros, if you leave a black GoPro at the pad in the sun, it will almost always overheat and shut off before you actually it has a chance to record everything. And I've had,
Mhm.
I don't personally use the run cams, but I know plenty of other folks that do, and so that's something else to kind of keep in mind. If it's in a shroud or whatever, don't use black. Print it out of something other than black
Right.
filament. Use or paint it white or something. You want to keep it all those electronics that are exposed to the sun as cool as possible because they tend to overheat pretty easily.
Mhm.
Yeah, we have like
Actually,
a decade
for that
old.
very,
We have like a decade-old GoPro, and that was the only thing that managed to capture video from the launch last year.
Yeah.
and then as for this year, for that very reason, the entire top of the rocket, including where the telemetry system is going to be housed, is all white.
Good plan.
Yeah, we're gonna do our best to make sure it doesn't overheat, but yeah. what will happen will happen.
Yeah.
So
But that's
okay.
good. That's good.
Okay, and I think yeah, that is about it as far as GPS and avionics go. Any other questions for kind of GPS telemetry and avionics sections?
No, so far so good. Everything looks really nice. Very good.
Right. Thank you.
Sweet. Now, there's not much left. Just go over some of the testing we've done. If you have any questions, let me know. We did plenty of carbon fiber testing, compression tests for the tubes themselves to help get different layer counts and thicknesses right, and verifying for FEA and modeling and simulation analysis so we can get those properties. We did also NDI to verify different manufacturing methods, get porosity and stuff for different ways of making the carbon tubes. That was something neat. Laser vibrometer, so the fin flutter test that I mentioned earlier. Obviously, we did ground tests. That helped us determine the charges and shear pin configurations. We did airframe modal testing and analysis. So basically, like the fin flutter, we did a very similar sort of thing with the whole airframe of the rocket to get vibrational modes and damping for the whole airframe. We did, the payload has done numerous tests, electronics and motor testing, resin testing to be able to cure under different UV light powers and wavelengths. We did the U-bolt tensile tests, altimeter sense testing, putting those in different vacuum chambers to compare how the sensors responded compared to each other. Battery drain testing, telemetry, link testing, and then we had our test flight on April 20th, just a few weeks ago, and it went very well.
Well, good. That's great. And the test flight is probably, I mean, that's the rubber meets the road. And if everything worked well and you weren't surprised, that's really a great. That's helps you portends well for the future. So that's a good sign there. But like I say, I would, since those Blue Ravens capture so much data, it's really worth going back and looking at that the apogee event and your horizontal velocity and the amount of shock forces you guys saw, the vehicle saw when the ejection charges went off and when everything hit the end of the shock cord. I find that always really informative, and a lot of teams are shocked. It's just the G forces are often much higher than they anticipate. I don't think it's going to be an issue for you, but it's just useful information. I think going forward, looking at other, when you start thinking about next year.
Yeah.
Let me look over my checklist real quick.
Yeah, and then after this, we'll hop on a phone here, and then we'll actually show you the rocket itself.
Okay. In fact, yeah, if you want to do that and wander over, we'll just kind of start at the top and walk our way back towards the rocket.
Yes, sir. Use my phone here.
And since it's flown, and with the amount of detailed information that's provided, I'm not super concerned, but I still ought to lay eyes on it or I'll get yelled at.
Oh, yeah, for sure. Okay. All right. Can you hear me?
Yep.
Sweet. That was nice. It had an option to just transfer the call from my computer to the phone. Okay.
That is nice.
So as I mentioned before, it is unpainted, or not fully painted. So she doesn't look as pretty as she will, but everything is there that needs to be. So just general overview. I don't know where, oh, we took the tail cone over there to show you. So tail cone goes on there. Oh, there it is.
Okay, so the tail cone, so the fins, that's a good body diameter. So there's a body diameter, it looks like, between the back of the fins and the back of the motor.
Yeah.
Okay.
Yeah, so this will slide on there like that.
Ah, okay.
And it meshes very, very well with this inner tube right here. So the brass retaining ring at the back of the motor casing fits almost perfectly here and just barely hangs off the back end of this tail cone. So there's
Okay.
so the exit, the nozzle is past the end of the
okay.
boat tail anyway.
Yeah, so a lot of times the nozzle's recessed into that, and you guys doing that will avoid that avoids all the issues I was concerned about earlier. So yeah, so seeing that is that's very useful. And so let's talk about motor retention. I assume then the motor is retained at the top of the motor.
Yes, so we've got centering rings here, 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 and then the motor retention. Sorry, this is from painting.
Okay, passes through that, and then you have a nut, I assume, that captures it.
Yep. So there's a bolt
Got
that
it.
is threaded onto, and that bolt is got a nut on the other side, a lot of epoxy, and then there's that wood bulkhead. The wood's on the other side, and then carbon fiber here, and then it's all fiberglass wet laid over the top,
Okay.
as well as screwed in through the tube walls. You can see this one screw here.
Ah, okay.
All right.
Now, but none of the recovery harness is attached to the motor. Is that correct?
No, the recovery harness. We talked about the counterweight bay.
Yeah.
So this is the counterweight bay right here. This is the coupler for it, and this coupler goes in between the booster section and the main tube, and this
Okay.
the U-bolt is attached to.
Got it.
And this is the main body tube section right here. And then this is the payload and drogue tube section. Those are joined by the avionics bay. This is the avionics sled that you saw the photo of right here. The batteries are currently out because, we talked about those. And referring to the charge wells, these are the charge wells we've used. As you can see, they're at least about twice as deep as the PVC end caps that a lot of people use.
Yep.
For the exact purpose of being able to contain the pressure a little bit better and give them longer burn time. The screw terminals make it easy to attach the E-matches after the AV bay is assembled, as well as all these XT60 connectors. Make assembly modularity very simple for us.
So are the wires all color coded?
For the most part, we had to make a few last minute changes. They will be in the once we finish on the wire changes.
Either that, or I would put labels, AA, BB, CC, just against. So when you show up at the safety thing, people aren't like, "Oh, you're going to plug the wrong one to the wrong," And so just make life a little easier for you at the safety review.
Oh yeah, for sure.
And yep, so the drogue chute is mounted to that big fat eye bolt right there. And then on the other side of this, there's this wood with carbon fiber centering ring right here in between those sections. And the payload is screwed onto that same bolt. And that bolt is fixed in there with nut and plenty of epoxy as well.
Okay. What's the diameter of the is that like 3/8 inch or?
I'm pretty sure it's a 1/2 inch.
1/2 inch. Okay. That's even better. Yeah.
It's tempered steel. I can't remember the exact alloy, but.
All right. That sounds pretty, I think you're in pretty good shape there.
Yeah, it is pretty hefty. All right, and then here on this forward end, so this is a cutout for the camera right here, as well as the telemetry pull pin or bolt holes, and then the nose cone will slide in there. There's the shoulder, some of these counterweights that go up in the nose cone, and then the tip is currently off. But then here's the telemetry sled itself.
So what are all the are those? What are those white things? They almost look like little battery connectors, or
Oh, these right here?
no? Nope, on that board.
Oh, this?
Yeah.
These are different communication and sensors. So this is the Pixhawk flight computer.
Oh, okay.
It just has so much functionality, and they build in all these interfaces to interface with different sensors and GPS and
Got it.
other communication protocol and things like that. That's what all those are.
That's good.
All right, where do you want to go and focus in some more?
I just have a couple last quick questions. How are those stainless steel weights retained inside the
nose cone?
nose cone? Yeah.
Okay, so the nose cone tip itself has this threading for a little rod. That threaded rod, so there's the nose cone tip, and then there's a little disc that goes inside the nose cone that holds the tip in there. And then we have a longer rod that extends below that, where these are fixed onto that rod. And then the bottom of that rod has a 3D printed disc that keeps that centered and from vibrating as well.
Okay.
And that just mates to the inside of the nose cone, just pushed up against.
So if that 3D disc were to fail, those wouldn't possibly come out through the opening at the end of the nose cone. Do they go in through the top or through the bottom?
They go in through the bottom.
Okay.
So they wouldn't come out.
Yeah, I'm just thinking, if a safety reviewer saw that, obviously we don't want any parts coming out of the rocket. And as long as if the failure mode was a 3D printed part, that they would still be retained in there. They just might move around, but
they would still be retained. All the 3D printed part does is keep them from kind of wobbling in flight.
Okay.
Through the top, like
no, they don't fit through the top anyway. They sit on the top.
So. Okay, perfect. Yep, I'm just thinking, when you're at the safety review, they're going to look for any possible, anything like that, and so you just want to make sure you had that off of the pass. What do you have covering the camera slot opening there?
Nothing.
Okay.
Right. Air cooled.
So air cooled, but so obviously that means that air will pressurize that compartment, right? Because you're going to have, as the air flows past it, it's going to either do one of two things. It's either going to create a vacuum, or it's going to pressurize it, depending on where and how the wind is flowing past there. You can get like a Venturi effect one way or the other. And so, is there anything in that compartment that will be affected by a change in air pressure, either positive or negative air pressure, as you got flight? Now, I know you've already had one flight, but that doesn't, just because one flight worked well doesn't mean that they'll all work well, right? So tell me what's going on inside there that might be affected by air pressure.
Nothing should. Everything in there is GPS.
Yeah, I'll come around to this side.
Just all the systems in there and the tracking.
There's no barometric pressure sensors.
Well, there is.
In the Pixhawk, are there?
There might be one, but we've just looked at the GPS data from it. So
there is the Pixhawk, but we never use it. We always just use the accelerometer.
GPS, and the accelerometer.
Yeah, so just in the telemetry system, just barometric sensor that we don't consider very critical.
Yep.
And then the payload itself does have some, a little fluid system to extrude the liquid resin through a nozzle. They have done pressure testing on that, and I don't have exact numbers on the top of my head, but it's not something that we are worried about.
Okay, good. All right. I just want to make sure that, again, from a safety review perspective, anytime you have air infiltration, you want to make sure it's not going to create an issue. So as long as you guys have a conduit for that, and as I say, as long as you can defend that hole in the airframe, that's fine.
Yeah. No, they've got check valves in the fluid system, and they've tested all the lines, and nothing fails until some absurd pressure. I can't remember what it was.
Last time.
All right.
Yeah. All right. What other questions or things that you want to see?
Let's see. I saw the pictures of the sled, and so we're in the rocket of the avionics.
So they're right here. So there's just a reminder: booster, main tube. So booster, counterweight bay coupler, main tube, avionics bay coupler with those electronics, drogue section, and then that what is it called? Bulkhead, payload, telemetry nose cone. So the avionics electronics will be all right here.
Okay, looks
Okay.
good.
That coupler right there.
Yeah. I think that's pretty much it. Everything that I've seen looks good. I really like the slideshow gave me most of the information I needed, and everything else that I've seen, pretty much you guys have been able to answer all the questions. So, of course, our main goal is A, to get you guys in the air, and B, get you recovered safely. And that's getting in the air part actually is really pretty easy. It's the recovering safely that appears to be the hard part for a lot of teams and for everyone. I mean, it's just up is easy, down is hard. Down safely is hard. And so that's really our goal here, is to make sure that there's no kind of issues in that. And especially since you guys are just going to 10K and you're subsonic, that's it's when you start hitting Mach 1.5, 1.8, that's when things start to get a little dicier in terms of structures and all that. But even that rocket, I think you guys could probably push that to Mach 2 without too many issues. That looks pretty good.
Tube failure strengths were pretty high.
Yeah. No, it's well, at Balls last year, there were a number of nose cones that failed at about Mach 2.7, 2.8, because when they were filament wound, there was a little bit of epoxy starvation, and so the angle of attack got high enough on them that they literally sheared about a third of the way down. And so, there's a lot of, once you start going fast, as you guys know, the forces, they're not linear, but they get big in a hurry. So well, good. Everything looks really good. I'm very comfortable. I don't think you guys have any issues. Just make sure that when you show up, you have all the documentation you need. You need printed copies of your checklist, and make sure that you should really have 3 checklists. Your arming checklist on the pad, your disarming checklist on the pad, so in case you have to stand down due to wind or you can't get tracking or something, and a safing checklist. The rocket lands, but all the charges haven't gone off. Just so that, because that's something that you're going to have to show. And they need to be printed. They can't be on electronic, because if you're out at the field, you may or may not have the electronics. And so make sure you have printed copies of all your checklists.
Yeah, we have a binder with all that in it, as well as all the altimeter manuals and things like that.
Perfect. Yeah, then I think you'll be in good shape. I will say I spent the morning working with a couple of Blue Ravens that after the latest software update just quit working. We couldn't not get Bluetooth connectivity on them. They were early serial numbers. And what's interesting is I have a couple of beta units, and they work fine, but Adrian saw a picture and he goes, "Oh, that could be because of the early serial number." So I don't know how old your Blue Ravens are, but test them and make sure that you still have all the connectivity you expect. I don't anticipate you'll have any issues. I think it's a really rare edge case, but anytime there's a new piece of software, and Adrian's got plenty of time to fix it, and I believe he's going to be there this year, since his stuff has become so popular with flyers, that I think he's going to be there, and we'll hopefully be able to provide some on-scene support. But
That'll be nice.
definitely double check your Blue Ravens the next week or so, just to make sure that they're still behaving as predicted. Because as you know, when the app kind of self-updates, it's hard to not have it update, and so sometimes it just be aware of that.
Yeah.
Just double check. Oh, one big change this year, we're going to have tents and tables available for you guys. We're getting these gigantic, huge, supposedly windproof tents. and we're going to provide tables, so you won't have to bring like an easy up or a table. You just have to bring chairs and other stuff, but not a table. You can always bring extra tables if you want, but we'll provide a table and a tent for you guys. So that is a big change from the years past, especially for teams that travel internationally. Not having to carry that stuff is a big deal.
Sorry, my mic was
I assume you
muted.
already had.
Related to that real quick, Tony,
Yeah.
is Ezra only providing one table per team? You don't know? That's okay if you don't know.
Yeah, that's terrible. I don't know, but that announcement should go out shortly, and hopefully
Okay.
we'll provide clarity on that.
Okay, another real quick question about that. Generators weren't allowed. It said in the announcement they are not allowed under the big tents that Ezra's providing. Do you know how they're recommending student teams get power to their setup areas?
That's interesting that you ask, because I've been involved in some of the discussions on that, but since I'm really in charge of the pads themselves, not
Okay.
that area.
Yeah.
And there was discussion that as long as that's, because of course the concern is buildup of exhaust gases under the tent and all that, which seems kind of crazy, but they got to be careful, right? And the chance of fire. So I think if they're located outside of the covering of the tent, they'll be okay. But I will ask about generators.
Okay. 'Cause, yeah, we were just curious if we could just bring a really long extension cord, or if we needed to bring like a large battery or something.
Yeah.
Or if Ezra was supplying power in some way.
Now, it'd be wonderful if we had power drops, but that's probably not in the cards for a couple 3 years at least. They are adding more power, but as you can imagine, adding power drops is extremely expensive. It's very expensive.
Okay, Scott, what were you gonna say?
At least from what I remember, I'm pretty sure they said 2 tables per team under the canopies in the first email they sent regarding that a while ago. At least from what I remember.
Okay.
And that actually matches what I was thinking. What I recall happening is if teams have above a certain number of members, they can get additional space and tables. I think that's kind of where the question was.
Okay,
but I'll verify for that.
Okay, the spaces should be about the same size though as last year, I imagine.
Yeah. Yes, they should be. Unless you have an extra large team, then I think they may assign you 2 spaces, but for the typical teams, they'll all be, I think it's 20 by 20 is the size of the space.
Okay.
If I recall.
Okay. I had one more question. I'm not sure if you would know the answer to this. This is relating to rocket labeling.
Yes.
Okay. You mind if I share my screen here?
No. In fact, I'm really glad you said that, because that's one of the main things I'm supposed to make sure is that you guys have your rocket properly labeled, and of course you don't at this point because it's not painted.
Here we go.
But I will say the numbering is a big deal. So
yeah, so we were just we had planned on doing this, but we were a little bit curious about a few details. So when it says things that could separate accidentally need to be labeled as well, like would you suggest labeling for example our AV bay, like is that like we can just put a label on one of the wooden bulkheads on one side of that, or would both sides maybe need it, or the sled itself? How I don't know.
Well,
small
I mean, at some point,
make these divisions.
Yeah, I mean, I hate to say it, after some flights, you'd have to label the individual components of the altimeter, but that's another story.
You got bigger problems at that point.
Yeah, exactly. Yeah. Really, the main thing is if the rocket were to break up in flight, let's say that you had a Kato, the motor Kato, or in the case of a high-speed flight, you had fin flutter and you lose a fin, and so the rocket turns sideways, high angle of attack, and it literally breaks at all the airframe. The airframe separates into pieces, which I've seen happen. At that point, if there's a piece of airframe laying there, they're going to want to be able to identify that section of the airframe. And so if it is, so in your case, each of the sections that you showed me that could separate, I think you'd want each of those sections to have the team number on it. because even though it's unlikely, it's possible that you could shear those screws through that carbon fiber.
Yeah. So like
It's
every
not likely.
separate tube and coupler, pretty much.
Yes. So your payload bay had a switch band, if I recall, and
yeah, the AV
trying to
bay
think
had a
about how
switch band.
yeah. So the AV bay itself, maybe on the coupler ought to have like with Sharpie the number, so yeah. So again, if you're at the table and if you're the reviewer, ask yourself, what would I expect if this thing comes apart? What are the potential pieces going to be, and how ought they be numbered, so that if I'm the guy walking out there and I come across this part, I can say, hey, this belongs to team 100, or 101 or whatever. So that's really the key. Is that yeah, for recovery purposes, if someone finds something, we know who it belongs to.
Okay, yeah, we will go ahead and do that. For some parts, we'll probably have
Yeah.
little stickers, and some we might Sharpie it on. We'll see.
Yeah, and that's fine.
Okay,
but the numbers on the airframe, the numbers on the airframe by the fins, those are critical that you get those correct.
Yeah, that is what I was really curious about. Scroll down to this appendix. Here we go. So when it says that it needs to be forward of each fin in the rules, does that say so we need to have like 4 labels of our number?
Yes, that is correct. And I know that because I did a 3D model of one that will be used in some of the live stream graphics, and I didn't, and I got yelled at. Like, what are you doing? You got to have the numbers right. And part of the reason for that is on live stream, because on live stream there's no way to know how your rocket will be oriented to the live stream cameras. And so when your guys' rocket is on the rail, and the live stream camera, it's a PTZ, pan-tilt zoom camera that's remotely operated. When they look at even though we know that pad 5 ought to be you guys, they want to be able to verify that by looking at that number on the rocket. And so that's really the main importance of that, is so that your rocket is correctly identified once it's on the rail by the live stream cameras. Because that's not used just for the live stream cameras, but the people at the LCO are also looking at that to verify, what's going on. If there's a misfire or a CATO, we want to know whose rocket it is, and so that's critical, and that's why, so that no matter how it's placed on the rail or what angle the live stream camera catches it, we can see those numbers.
Okay, that's good to know. That's important. So it'd be kind of funny for us because it's just 1-1. It's like this one little straight line down above every fin.
Yeah.
All right. Those I think were all of my questions regarding the labeling. So thank you for answering those.
Yeah. And it's and it is the live stream actually has become a big part of this. There were a lot of viewers. It has gotten us a lot of, I don't want to say notoriety because that's kind of the wrong word, but it's gotten us a lot of
some street cred.
Yes, and especially with the New Mexico folks, because the fact that there's so many people watching it, it gives us some extra leverage, and so we're really working hard. In fact, we're really spending a lot of time and money and energy on improving the live stream quite a bit. We're going to have a lot more information. Like, we'll have the date and time for once, which we didn't. So if you go back and you watch replay the live stream, it's like, what time of the day was it? No one knows. But we're doing a lot of that. We're going to have a lot more real-time data, real-time weather, and so there's a huge amount of energy that's being placed on on improving the live stream, especially since so many teams are from overseas, and they're people back home want to watch it, and so it really, the numbers that we get watching it are pretty interesting in terms of they're a lot higher than most people expected, and so that's one of the main reasons for that, getting your numbers on there so we know exactly whose rocket is flying.
Awesome.
Yeah. And get your flyer record. You have your places to stay. I assume you already have your travel, all that kind of stuff done.
Yep.
Make sure that you have plenty of food and water, all the stuff. You guys have been there and you're from the area, so that's not anything I shouldn't have to worry about. I'm just making sure there's just a few things on this list that I'm supposed to go over. Okay, so the flyer of record was on the remind me who the flyer of record is. That was Scott, right?
That's Scott, yes, and he's been on here the whole time.
Okay. Yeah.
Thank you, Scott, for staying on.
Yes, thank you. I just need to make sure I mark his attendance on my sheet here.
Oh, okay, perfect. Yeah, I've been listening the whole time. Don't worry, I was not driving home that entire time. It's not that bad of a commute from work.
Yeah, I've made that drive before,
Yeah.
Scott, so I know it's only
Yeah.
25 minutes or 30 for
25 oh,
you,
no.
actually.
It's,
Yours is like
45
30,
for me.
35. Oh, really?
Mine's 45 because I go from Briggs all the way back to Round Rock.
Oh, yeah.
But it's
All
All
good.
right. Well, I think we're in good shape, and congrats on having a successful test flight. That's always a big plus. Sadly, I've seen some very unsuccessful test flights of teams that end up without a rocket to take because the test flight a month before doesn't go so well, and that's a pretty hard pill to swallow. So I'm glad you guys are not in that boat. Everything else looks good. Make sure that you have a good handle on the labeling. At this point, I can't sign off that it's properly labeled because obviously you got to paint it. But the fact that you asked me those questions tells me you guys are well aware of that, and I'm not concerned. So
Yeah.
All
Thank you,
right.
Tony. We appreciate your
Excellent.
time.
Yeah, well, good work. I look forward to seeing you guys there, and safe travels and good luck at the end of the school year. I know it's a busy time for a lot of folks, and so good luck with everything.
Sweet. Thank you. We passed the
All right.
FRR. Good job, everyone.
Yeah, excellent job. And I liked the slideshow. That made my life a lot easier because you covered almost all the information I wanted to see, and so the visual part of it was a lot easier for sure.
Yeah, it was pretty quick. Last year's was a little bit longer. I remember that.
All right.
Awesome. Thank
Well,
you,
good.
Tony,
Yeah.
for your
Yeah.
time, and
Yeah.
thanks for
Yeah.
staying on and staying easily to reach over email too.
Well, good. Yeah. Anything else? And I'll try to verify that information. I wrote your questions down, and I'll try to get an answer to you on that and get back to you. So that's stuff I should know, and I just, if I knew it, I forgot it. I've got so much stuff going on, as you can imagine. We're trying a lot of stuff to get ready, but
Yeah.
So, okay. Well, thanks, guys, and good luck, and we'll see you in a few weeks.
Thank you. See you too.
Thank you.
All right. Bye.
Nice job.
Nerd.